AS913 chemists, welcome to TP's Chemistry Cuts. In this bonus clip we work through two different types of questions involving calculations of buffer solutions. The first type of calculation involves mixing a solution of a weak acid with a solution of its conjugate base.
Again, this is a bonus track for you, and what we're doing in this one is just mixing a generic, if you like, weak acid solution with a known volume of its conjugate base. Okay? And so really the only issue in this type of question is the fact you're mixing two solutions. Okay? Not adding a solid to a solution, you're mixing two solutions. And so you're going to get a dilution effect because the volume in the mixture increases, but the amount in each component stays the same. So if you're increasing the volume but keeping the same amount in the mixture, then you're getting a dilution effect. So what we need to do first with this is to recalculate the concentrations of the two substances that are going to be in the mixture. Okay. So let's do that. Okay. So we'll take the concentration so the new concentration is equal to the old concentration times the original volume over the total. And remember, you don't need to worry about units for the volume because they are self-cancelling so long as they're consistent. So if we look at the concentration of H but to begin with, and don't worry about the but part of it, we'll look at that later. That's equal to the old concentration of H but, which is 0.45 moles per litre, okay, times the original volume, which is 300, divided by 800. Okay, so I'll put it all in full so you know where the numbers come from. And if somebody can calculate that, well, I go on to the next one, which is but minus. That's equal to the original concentration of that is 0.25 times 500 over 300 plus 500. If somebody else can calculate that.
The first one 0.169.
0.169.
The second one 0.156.
0.156 mole per litre. So if before we start, you can see they're very close to each other. So if they've got similar concentrations, if they were the same, what would be the pH? When you have equal concentrations of the acid and its conjugate base in a buffer, what's the pH? It's equal to the pKa. Remember that? You need to go back and look at the last instalment on YouTube. Okay, so now once we've done that, we've been given a Ka here, so let's write out the expression for it and the equation for it, and this hopefully will make it clear what that actually means. So I use these funny things because it's a lot easier just to make up numbers. It's no real acid, but it's just going through the process of doing the calculation for it. So if this is an acid, a weak acid, when you add it to water, it's going to lose that proton to water to form H3O plus and BUT minus. So that's an anion. So in solution, we're just putting sodium with it. Okay. As the counter ion. Right, so the Ka for this is equal to the concentration of BUT minus times H3O plus over concentration of HBUT. And once again, look what the question's asking you for. We're going for the pH, so which part of this expression needs to be the subject of it? H3O plus. So if we rearrange this, it's Ka times H divided by BUT minus. So Ka is 1.51 times 10 to the minus 5. H but is 0.169, and that's divided by 0.156, which is
1.64 times 10 to the minus 5.
so that's the concentration of H3O plus. So the pH is equal to minus the log of that.
Four point seven nine.
4.7. Okay.
This second calculation involves adding a solid conjugate base to a weak acid solution.
Right then, so where would we start with this? Equation. Good. So let's do that. HClO2 So the next thing is to work out what we've got. We've got Ka. We've got the concentration of HClO2. We don't have this one yet, and we don't have that one yet. But we do have a mass of this. We're dealing with equations here, so equations, when you derive expressions from them, always deal with moles. So if you see any problem where you're talking about a mass of something, you must first convert that to an amount in moles. And then it becomes applicable to the expression here, which talks about things in terms of moles, moles per litre, but it's the first step to put it into moles. Yeah? So, N is little m over big M. Our little m is the mass of sodium chloride, I think it is. 5.25 divided by 90.4. So we can calculate that.
0.0581.
0.0581 mole. Thank you. Right. And that is being dissolved into 750 mils of water, which is what we've got as our starting. So we can work out the concentration. So it's somebody could calculate that.
Zero 0.0775.
So now we have that. Okay.
Just change this number.
So we now have everything we need to work out the concentration of H3O+. So rearranging the above expression is equal to Ka times the concentration of HClO2 divided by ClO2 minus. So that's 1.1 times 10 to the minus 6 times the concentration of HClO2, which we are given up there, which is 0.104, and then we divide it by 0.0775. Somebody calculate that.
1.48 times 10 to the minus 6.
48 times 10 to the minus 6 moles per litre. Once again, don't forget your units. Then the pH is equal to minus the log of A3O plus, which is equal to minus the log of 1.48 times 10 to the minus 6.
5.83.
5